butene. So this would be 1, 2, 3, 4. This would be a 2-butene. Cis is the sense that both of these methyls are on the same side. And what we're doing is we're reacting this with, very specifically, metachloroperoxybenzoic acid. And so, as a result of the mechanism of this reaction, the stereochemistry on the alkene is preserved, meaning that the oxygen goes down on one face or the other, leading to the stereochemistry of the alkene being the same. So that means that the only epoxide you would get back from this would be where you have both methyls on the same side. So that would be one of the products, and of course we could form the epoxide on the bottom face, but again you'd still get the same methyls being on the same side. So this is a nice example of how when you have these alkenes, when you do epoxidations, you preserve the stereochemistry. Okay. So in this particular case here, we're now starting to leave the gate on doing multi-step reactions, meaning that because you know how to create certain groups from alkenes, you can take those groups and change them in sequential patterns. So for example, if I gave you this simple alkene, we could take, for example, we could take Br2 and water. An alkene plus those reagents, of course, give us the halohydrin. So in this case, I would always get an alcohol in the Markovnikov position, and I would get a bromide on the other side, creating a halohydrin. I could then take that halohydrin and react it with, and I think last time we used a sterically hindered base, such as pyridine. So remember, pyridine was this nitrogen-containing base that looked something like this. And what that allowed us to do is take a halohydrin and create an epoxide from it. And then, of course, if my end product was, let's say, a 1,2-diol, I could take what we learned at the very end last time, where I could take some sort of acid and hydrate epoxides through an acid-catalyzed mechanism to come back with and of course, because we're creating a chiral center at this point, that would be creating a racemic mixture of this particular alcohol right there. So in this case here, we also created a racemic mixture. I should probably be pretty accurate on that one, where I had a racemic mixture here. I then created a compound that then had another chiral center, so this is still a racemic mixture here. So once you've created the racemic mixture, you keep on reacting with both components to again get to the final product there. So I use this as an example of the fact that all the reactions you're learning, you're going to be expected to now build reaction schemes based on either knowing the starting materials or knowing the product, and either working in the forward direction or working in the backward direction using all the reactions that you know. So that's like the big goal of this class, and that's how all these reactions add up. So I just want to give that as an example. So in this particular case, we end up getting back, if we do an acid-catalyzed hydration of an epoxide, we get back diols that are anti, meaning that the alcohols are on opposite sides of this particular molecule. Well, there is only one way in which you guys can create diols that are on the same side, and that is using osmolation. So in this case here, this is a reaction. All these reactions were shown last class on the board. And so in this particular case, we can do a hydroxylation of an alkene using osmium tetroxide. So in this case here, if I have this particular, actually we'll use the alkene that's on the board there. So we'll do this alkene like this, and you were to expose it to osmium tetroxide, which osmium is in its +8 state, which means that this is a highly oxidizing agent, which will now, of course, oxidize those carbons, and you do that in the presence of pyridine, which is a base, you can create the cyclic osmate intermediate as a result of this reaction. So what actually occurs here, if I was to show a mechanism as we go through this problem, here's our alkene. Here is our osmium compound, so OS, O, O, O. So we have our osmium, we have our alkene, and so what ends up happening is that the alkene attacks one of the oxygens. The reason why this attack even occurs at all is because of how oxidizing that osmium is. It's dragging electron density towards it. It's very electron deficient. As a result of this, we can move electrons up onto osmium, and as a result, we can then attack back with the other pi bond on osmium to come up with our osmate ester. And the reason why this is happening is because this osmium compound is flat, which is the reason why we're getting a syn addition of the alcohols, is because this particular arrangement of oxygen, osmium, oxygen is flat, just like the alkene is flat, which means it can only attack one side or the other side, which leads to this. So in this case, if we attack from the top side, that means that both methyls go back, and we end up getting an O, osmium, O, and of course this would be wedged up, even though it's a little bit artsy there. O, O. And then what we then need is a reagent to reduce the osmium off of this compound. So in this case, we use sodium bisulfite. So the reason why the sodium bisulfite's there, we're not going to push arrows for it. So HSO3 in water is that this reagent reduces the osmium, which allows us to remove the O's that we attached in this step in one step at the end of the problem. So in this case here, we do a reductive workup, and what that leaves behind, of course, is then the OHs on the same side of the molecule and the CH3s on the back side. So that last step with the bisulfite, it has nothing to do with the carbon structure, it has everything to do with the osmium, and it reduces the osmium off, leaving behind a syn diol. So this is one of the only ways in which you can create 1,2 diols that are syn, being on the same side, and you're going to see why that's important to have syn diols in just a second. Any questions? Okay. Oh, I'm sorry, go ahead.
I know that this goes back a lot of lectures ago, but can you repeat like the direction of the arrows? How we know that the arrows go like to that carbon and that bond goes to oxygen?
So in many cases, each one of these reagents have their own specific arrow pushing, but behind this though, it starts with what I said first, which was osmium is in a +7 or +8 oxidation state, which means it's electron deficient. So how did I start my arrow pushing? I took that pi bond and I attacked it, right? So at the end of every one of these complex mechanisms that I'm doing, there's always the idea, I'm staying true to form, that I'm moving electrons where the electrons are at to where the electrons are not. And that's exactly what drives this chemistry here. Okay.
And how do you know, because on the homework it was like if it is like the lone pairs to the carbon, or like from the bond to the carbon, how do you know it's like, or from the oxygen to the carbon?
How do I know this one here?
No, just whichever, like in general, because in the homework it was like the oxygen and then the lone pairs.
Right, so in this particular case, the reason why I know it's attacking oxygen is because of the end product. So in the end product, I know I'm getting back alcohols. Those alcohols and those oxygens came from the osmium, which means that this particular intermediate, the oxygen has to be attacked and the oxygen has to do the attacking. So leave behind this. Okay.
Thank you.
Yep. Okay. Done. All right, next one. Have I mentioned this class is kind of like a runaway freight train once you get out of chapter 5? I probably haven't said that yet. That's where we're at. We're on the runaway freight train all the way to the end. So now that we've created syn diols or have the ability to do that, we can actually use other reagents to now cleave alkenes by creating the 1,2 diol. So in this particular case here, alkenes can be cleaved into ketones, aldehydes, and carboxylic acids when we use the appropriate reagent if you have, in this particular case, syn 1,2 diols. So this reaction here uses a periodate reagent, and it starts with a syn 1,2 diol. So this allows us to do this. So using that osmium chemistry, we can create syn diols. In this case here, we're going to use this one. So OH, OH, and then there's just an H here. And if we were to use periodic acid, HiO4, in water with a little bit of organic solvent, in this case we're using that cyclic ether tetrahydrofuran, we end up getting back a cyclic periodate intermediate. And so if I was to describe the mechanism for this reaction, so let's see, we have this. We have our syn diol, so OH, OH, this is a CH3, I'm not going to worry about the other one. So what ends up occurring is that you have now IO4, which is OH, O double bond, and then in this case here, we have also O, so that would be O here, O there. And so what ends up occurring, well, through the reaction here, so it's HiO4, that's a double bond there, that this oxygen ends up attacking the iodate. This ends up then breaking this bond here, so then this then attacks back here, which then creates a cyclic or iodate intermediate. So in this case here, it has to be syn because of the transition states. So that'd be O, O, I double bond O, OH, O, double bond O, like that. 1, 2, 3, 4, 5, 6, that makes sense. And then what can occur at this stage is that now, because we created this cyclic periodate ether, we can now break a carbon-carbon bond. We haven't done that yet. Organic chemistry is the making and breaking of carbon-carbon bonds. So if I'm going to break or make a carbon-carbon bond, it's a big deal because they don't break easily. So in this particular case here, we have this intermediate that drives the breaking of that bond. So in this case here, we're breaking the carbon-carbon double bond to create a double bond here. We're also then moving these electrons onto iodate, and then this then moves back down onto here, which then results in the breaking open of this ring into a, so I'll break it this way to make it easy to see, and then I'll draw it a different way in just a second. So according to the arrow pushing I just did, that leaves us with this. So now this would be double bond, and of course there was a methyl on this side and there was a hydrogen on that side. That becomes important now because now I make a ketone up top and I make an aldehyde on the bottom. So by having a syn 1,2 diol I can take this proiodic acid, I can now cleave a carbon-carbon single bond to then create now ketones and aldehydes as a result of it. I can also draw this a different way. So I can draw it this way. So this would be CH3, C double bond O, and then we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That would be another way I could render that to you. Because of course we know that this has eclipsing hydrogens. This would be the completely staggered form if I was to roll it completely out. And this is the first case in which we were able to cleave a carbon-carbon single bond, which is super important. So the finish to this piece right here would be double bond CH3, and then double bond H. So what's another way to think about this type of cleavage chemistry? Well, if you have syn-2,1-diol, so for example, the bottom example there, if you see the reagent of proiodic acid and water and THF, what you end up getting back are, in the bottom example, ketones. This example here, we got back an aldehyde because the substitution pattern on that carbon was a hydrogen. But if you look at that second example up there, where we have this, we have a 1,2-diol that has carbon substitution on both carbons, and I expose it to proiodic acid in water with a little bit of organic solvent. What I'm actually doing is, of course, cleaving the single bond between those two groups. And everywhere there's an oxygen becomes a carbonyl, if you look at the chemistry that's shown in that mechanism. So in this particular case here, that bond would break, leading to, of course, 2 moles of the ketone. Any questions with that one? Yeah.
So what would the arrow pushing look like for that?
For that one there? Yeah, let's see. So after reacting with proiodic acid, that ends up leading to this cyclic intermediate, so that would be this. Whoops. O, I, double bond O, double bond O, OH. And then this would be from the other one, so that's O to there. I think I got it. So this would be the intermediate that occurs from the part of activating it with proiodic acid. And then to break it open, what would happen would be this single bond would break, forming a carbon-carbon double bond there. That would move electrons onto iodine, and then in this case here, that bond would break, forming now the double bond on the other side, which then creates 2 moles of that. Did that get there?
Yes.
Okay. Okay. Yes? Okay. Well, there's other ways in which you can cleave alkenes to get back oxidized or carbonyl-based compounds, either ketones, aldehydes, and at the very end we'll be getting back carboxylic acids. Each one has their own path. Some of them will have mechanism for them, some of them will just be the memorization of the reagents that are being used. So in this case here, we can take ozone. So ozone is a really reactive oxidant that is not naturally occurring, but if you put oxygen into a high electric field or a plasma, you can actually get back ozone. And that ozone can then be used to cleave alkenes, oxidize other types of inorganic and organic compounds. And so in this case here, the reaction that we're doing is we're taking an alkene. We'll use our generic alkene. And we're exposing it to ozone in the first step. And then in the second step, we're reducing one of the intermediates with metallic zinc in, it appears to be acetic acid plus water. And so using these two sets of reagents, what that does is it cleaves the double bond, leaving behind what groups are on each one of those carbons. So in this case, I would get back an aldehyde from the left-hand side. So this would be the product from the left-hand side of the alkene, and then also get back formaldehyde from the other side. So the way to look at this is that when ozone attacks this alkene, wherever that double bond is at, you're replacing it with a C double bond O. And you're leaving behind the substituents or the groups that are on that alkene. So I'll just draw them out right here to kind of call out why two different structures were shown. So what is this mechanism? Okay, so let's see. So ozone. Lewis dot structure for ozone. That's reacting with this alkene, so we're going to go with alkene here with the CH3 on it. In this case, we have O minus, O neutral, so this will start with the O minus attacking one side of the alkene. And of course, as a result of that attack, the pi bond breaks and attacks the other side of the ozone, which then of course moves the electrons to the electropositive oxygen and leads to the first intermediate, which is what's called a molozonide. So in this case here, what we create is this. So O, 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 and then this would be where my CH3 is at, and then this would be the other side of the molozonide. Let's put electrons where they need to be. So let's see, we got that one, we have that one, and this one. Okay. So now what happens? Well, the molozonide is going to break apart. So in this case here, what ends up happening is that single carbon-carbon bond breaks, which ends up pushing electrons onto the oxygen there, and as a result, forming a double bond here. So let's see, so that goes double bond there, that breaks. This then goes to, actually this arrow here is going to go to there. That should work. Okay, so then what this then creates is this intermediate situation. So what I have is C double bond O CH3H. That comes from this side. And then on the other side, I have now C, H, H, O, and then double bond O. I'm just thinking I want to sweep one of those electrons, but I can't. So we're going to go with this. So then that would be 1, 2, 3, 4. So that would be neutral. This would be 1, 2, 3, 4, 5. That's a positive. That's now a CH2, H and H. Oh, I had it right the first time. Gosh darn it. Okay, hold on a minute. So this is going to go like that, and this is going to go like that. There it is. I was like, my God. Okay, so we have this compound that then forms the molozonide. The molozonide now breaks apart to form that acetaldehyde plus now this compound here. So that'd be O minus O double bond to C, H, and H. And this, of course, would be a minus. This, of course, would be a plus. Woof. Okay. So now that this happens, now we're on our way to form the ozonide intermediate, and what ends up happening is, I'm gonna have to restructure this. So in this next step, it looks something like this. This would be CH3, double bond OH, and now we have O positive C, H, and H. And now what occurs, because we have now this peroxide entity right here, that one of the lone pairs attacks that carbon there. This then allows us to create a oxygen-carbon-oxygen bond, and then as a result, that lone pair of electrons goes up to that oxygen there. As a result of that arrow pushing, we end up getting back now our ozonide intermediate, which is slightly more stable than the malozonide. So in this case here, what would that look like? So we'd have a CH3 and an H and an O to a C that has an H and an H, and then we have O, that. And this would now be our ozonide. Ozonide. And now that we're here, now we come in with zinc and some sort of acid with a little bit of water, which this zinc, of course, is zinc 0. That's going to be a reducing agent. And what that does is reduce this compound, or this ozonide intermediate, into the two different products, which in this case would be the CH3H and the C double bond OH and H. Now, I'm not going to push arrows for single electron transfer from zinc. This is an introductory course. This is an advanced organic. But the bottom line is that as soon as we get the ozonide, the zinc is then reduced, and that then leaves behind carbonyls. And the carbonyls have the structure based on what was bonded to the original alkene. So by doing ozonolysis with a reductant workup, you get back, again, mixtures of aldehydes and ketones, depending on what's bonded to that original alkene. In the case up here, where we have methyls on each one of these groups, we get back what? We get back methyls on each one of the carbons, and of course carbonyls replacing where the double bond is at. So the mechanism for this reaction is shown here, and the creation of that ozonide intermediate. And this slide actually does a nice example of kind of expanding out what does this mean for you. So in this particular case of the top one, where we have a tetrasubstituted alkene, if we use ozone and then work it up with zinc 0, we end up getting back a mixture of the two ketones, right? So we have tetrasubstituted, which means we have this substitution, double bond, and then of course these two methyls come from the other side of the alkene. Down here, we would be breaking these two bonds here, which of course leads to aldehydes, because we see we have hydrogens on each one of those carbons. Any questions with that? Okay. We can go even farther with this. And so in this particular case, we're going to a partially oxidized form of carbon in the sense that we're getting back aldehydes and ketones. But if we were to use a rip-roaring oxidant like potassium permanganate, we could take these alkenes and take them all the way to carboxylic acids and even to the most oxidized form of carbon, which is CO2. Okay, so what are we doing here? So this is another set of reagents. In this particular case, let's use our generic alkene. If I was to come in now with potassium permanganate or manganese 7, again, highly oxidized metal in the presence of some acid, I could use anything for this. What this does is it cleaves the alkene, and if there are hydrogens on the alkene carbons, that results in carboxylic acids, the most oxidized form of carbon. So in this particular case here, when we think about this cleavage reaction, what we get back, because there's a hydrogen on that carbon, and because there's hydrogens on that carbon, what you end up getting back from the left side would be acetic acid, and on the right side, we end up getting back CO2. Now the reason why we get back CO2 is because we have two hydrogens on that carbon. In this case here, we get back a carboxylic acid because we still have an alkyl group on there which can't be oxidized by the permanganate. So if I was to do something like this, so let's do another example where we have this alkene and I expose it to potassium permanganate in some sort of acid, then what you get back is the cleavage of that alkene, and I get back, of course, the carboxylic acid with the methyl group on there, so let's call that out. And because again, I still have a hydrogen on that carbon, that means I'm going to get back a carboxylic acid. So in this case, that would be this one, CH2, CH3, C double bond O, OH. And we'll do the last one. So in this case here, if I use that exact same alkene, but now I put two groups on that right-hand side, and I expose it to potassium permanganate, which ends up catalyzing this cleavage reaction. Well, what do I get back? Well, on the left-hand side, I still have a hydrogen there, and if there's a hydrogen on the alkene, that side gets oxidized all the way to the carboxylic acid. So I still get this from the left side, but on the right side, I don't have a hydrogen on the alkene anymore. So that would then give me back a ketone. So what's important for permanganate is the fact that if you have hydrogens on the alkene, that takes it all the way up to the carboxylic acid. And if you have two hydrogens on the alkene, you end up going all the way to CO2 as your product. But if you sequentially start to remove those hydrogens in the alkene, you see now we're getting mixtures of products between ketones and carboxylic acids. Yeah, go ahead.
Is that the mechanism for that?
No, yeah, so we're not gonna do that one. Yeah, so in this case here, it looks a lot like the osmate mechanism, but the bottom line is that that's meant for later organic chemistry classes. In this case here, I'm just introducing the fact that if you use an oxidant, this set of reagents gives you back carboxylic acids. Pushing arrows for this is a little bit beyond the class.
Okay.
Yeah.
So does it basically go 3 hydrogens too and then just 1?
Right, so I was trying to show, of the different scenarios with permanganate, if there's a hydrogen there, it goes to the acid. If it's not there, it stops at the ketone, because you need the hydrogen to drive that reaction all the way to the OH. Okay. So, what would be the products expected from the reaction of 1-methyl cyclohexene and aqueous acidic potassium permanganate? Let's see what we got. 1-methyl cyclohexene. So here's cyclohexene. That would be 1-methyl cyclohexene. We're using potassium permanganate in some sort of acid. You guys know now that if we do that, that means I'm cleaving that bond and I'm replacing that double bond with a double bond O. And if there are hydrogens on that carbon, it goes to the carboxylic acid. It gets all the way oxidized to the carboxylic acid. So if I was to draw this, keeping with the cyclic structure, the top one would look like this. So of course we get back a ketone from the top one because we have a methyl on there. Now for the bottom one though, we would get back O and then OH. And of course I could draw this into its linear form as well. So C double bond O. Another way to draw the product would be this: 1, 2, 3, 4, 5, 6, double bond O, OH. Again, sticking with the rule of if there's a hydrogen on the alkene, that carbon gets oxidized all the way to CO2. If there's two hydrogens, it goes, oh, I'm sorry. If there's a hydrogen on that alkene and an alkyl group on the other side, you get back carboxylic acids. If there's two hydrogens, you get back CO2 from the alkene. Any questions with that? Okay. The last reaction that we talk about is a really interesting species, chemical species, because it violates the octet rule for carbon. So there are carbon intermediates called carbenes. Carbenes are neutral molecules that have only 6 electrons in the valence shell of carbon. So a carbene technically would have a structure of this. So even though we hem and haw about the fact that carbon always wants to maintain an octet, there are reactive species such as carbenes that can be stabilized or created in reactions and be used with alkenes to create cyclopropanes or chlorocyclopropanes. So in this particular case, if we have a carbene structure in an alkene, we get back cyclopropanes, which are 3-membered rings with carbon in the middle. The reason why that occurs is because of the fact that we have this lone pair in an sp2 orbital, which allows us to react with the pi bond of the alkene to create in a concerted way, meaning all in one step, a cyclopropane. This is very reminiscent of the carbocation, which is also sp2 hybridized. So in this case here, we see we have a vacant orbital above the atom. The same thing happens with carbenes. Makes them amazingly reactive. And so if you can create a carbene, carbenes can be used to cyclopropionate alkenes. And so this particular cyclopropionations are stereospecific, meaning that if you have a cis alkene, you're going to get back the alkyl groups on the same side of the cyclopropane, just like what we saw for metachloroperoxybenzoic acid. That was the same type of reaction. So in this case here, what do we have? We have C, double bond C, and we have H. I'm going to shorthand that as ethyl. So ET is just me shorthanding ethyl up there, the CH3CH2. Here we have H, and then over here we have a CH3. And in this first reaction, we're creating a carbene in the reaction. And I'm going to show you the mechanism for this in just a second. Actually, no, let me show it to you now. So we have here an alkene in chloroform with KOH. So what's the mechanism for this? Well, it starts off innocently enough. So we have here chloroform. So there's chloroform. Carbon has all these chlorines pulling electron density away from that carbon, which makes that hydrogen very acidic, which allows me to come in with a strong base like potassium hydroxide. The hydroxide comes and deprotonates the chloroform in the first step. So in this case, this kicks out water and leaves behind a carbon with a chlorine and a chlorine and a chlorine and a lone pair. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That would be a negative charge there.
It is ET.
And as a result of having these chlorines being such electron-loving groups, the next step is it eliminates chloride. So we're able to stabilize this carb anion. As a result of the negative charge being on carbon, it allows us to kick out a chlorine because they want electrons more than the carbon structure, which leads to our chlorocarbene. Yeah.
Does that say ET on like the initial thing?
Yeah, so that's my shorthand for ethyl. So
Oh.
ET is equal to ethyl, which is summarized that CH3CH2. Yep. Okay. Now that we have the carbene, now it can react with the alkene. So at this point here, the alkene comes in. So we have here the ethyl group coming out, the H going back. We have an H going back, and the CH3 coming out, and then that attacks there. The alkene attacks back, which leads to then the chlorocarbene, meaning that we get now a chlorocyclopropane, and as a result of that mechanism, all of the regiochemistry is preserved, meaning that we started with a cis alkene, and we end up with a cis cyclopropane. And the reason why we could get there with this particular reagent is because that hydrogen's so acidic, those chlorines are so electrophilic, that allows us to stabilize this unstable species, this carbene. And allows us to cyclopropanate. And of course, because we're attacking something that's flat, this carbene can attack from the top side just as easily as it can attack from the back side as well. So it's a very stereospecific reaction and happens all in one step in that last step. That's the we just did the mechanism there. Any questions with that? Okay, last reaction for alkenes, and this is a named reaction. So this is the first named reaction we're doing. It's called the Simmons-Smith reaction. It is an organometallic reaction. So I got my PhD in organometallic chemistry, and the cool thing about metals is that it stabilizes unstable species if you get the right mixture of metals. So in this particular case, if I use diiodomethane plus this zinc copper amalgam, it creates a carbenoid-like species. So what it does is it inserts a CH2 from that diiodomethane into the zinc, which stabilizes this unstable carbene. And then by adding this set of reagents to any alkene, you end up getting back now cyclopropanes. So in this reaction here, you get back chlorocyclopropanes. In this Simmons-Smith reaction, we get back literally cyclopropane using a very similar mechanism, but certainly nothing that we're going to push arrows for in this class. So if you see that set of reagents, that creates cyclopropanes. That's pretty much the level that we're at. Any questions? Okay. So, with all that being said, if I gave you that alkene and those sets of reagents, what would be the product that you get with some stereochemistry involved? Like I want to see wedges and dashes. So take a minute and draw what the product would be from that particular reaction.
Until 4 a.m. So okay, we have a page. You're not looking too good.
Bond is where it's going to create this
Now notice in this alkene, there is no stereochemistry given to you, so you can pick it. You can go cis or trans, and either one would be right. You have to pick one of them, though. If I don't give it to you. So in this case, I don't give it to you. Keep on going.
This reminds me of
And then,
And then we said
Because we don't have it yet. Maybe I'm wrong, but.
Oh, so we're using.
Something like that, but like hard.
Something like that.
I know that.
Yeah, so it'll come up as
Oh no.
but we have to.
I knew you were gonna.
Exactly.
So you have to add the switch.
Me? Thank you. 100%.
All I did was draw them out.
Just because you might not have had it in your notes right away.
It's added to the first big thing. Never mind.
No, I don't know what I'm doing now.
I'm actually.
No, I should stay.
So you made a trans alkene and then you guys are gonna do cyclopropane?
Yeah, I think it would take like
Once you have the alkene, then you wanna put you wanna make the 3-membered ring on yours.
Our marker doesn't.
Oh, no.
like a sorority. Like
Irina, you wanted to make one, but you couldn't.
I had to do
Okay.
it.
No. Oh my god.
Argentina.
300.
Argentina. Did not win. No. Good effort.
2. I have 2.
We're not, we're drawing the
My
mechanism
last
meeting.
question
Tax
called.
cards, so it's already taxed back.
If I ask my question, like, please text me when you have a question. You call me like, do you answer? Sorry, I'm
That
confused.
did it.
Down right now.
The only thing that gives me a little bit of pause is that you can't dash and wedge that alkene, meaning that methyl has to be flat.
He's a retired chemist.
No, the upper one.
Oh, this one?
No, the first structure.
This
That one. Right, so on the alkene, you can't wedge something off of a double, no.
Just text me.
You were okay with the, I mean,
No, that one has to be
You were on the
straight.
phone with him on that night, and I was like, don't do it. And then we realized Alyssa was
no. Yeah, so I see what you're saying. So like that would be, if that was that way, then one of those has to be wedged or dashed out. So like that's more of a nuance. I was more worried about the alkene, where that had to be flat.
Oh, this one has to be
Right, if you put it in the
flat.
plane.
This one, it doesn't matter.
Yeah.
Oh, okay.
Okay.
Thank
Yeah.
you.
Okay, I think
We're in this together.
I see good structure. Yeah, I see it. Yeah, you guys are getting there. So if you have that alkene, all you're doing is taking that carbene and just snapping it onto one of the sides of the alkene and it doesn't bother.
And this one will be a ring string?
So that would have a lot of ring strain, but then it would be, I like how you presented the stereochem. Okay, so in this particular case here, I didn't give you a particular stereochemistry of the alkene, which means you could go with either cis or trans, but what's important is if you cyclopropionate it, the stereochemistry is preserved of the starting alkene. So if it started trans, it better be trans. So in this case here, I have a trans, I decided to do the trans isomer. I cyclopropionate it, and that basically creates a 3-membered ring where the alkene was at, but all of the stereochemistry was preserved, meaning that if this isopropyl group was sticking out, then that methyl had better be going back.
Yeah.
Yes? I hope. Okay. Okay.
Wait, how do you know that it's supposed to be a 3-membered ring?
From the reagents that are being used. So in this case here, the set of reagents would be the Simmons-Smith reagents, where we have diiodomethane plus the zinc copper amalgam. Gives you a carbene, and that carbene does the exact same thing that chlorocarbene did, where it adds to one of the faces, creating a cyclopropane.
So that's just like knowledge that I should have in my brain.
This whole, yeah, you're just building reaction after reaction after reaction of different things happening.
Okay, word.
Yeah.
Word.
Okay.
You're just supposed to know.
Okay, so that ends chapter 8. At the end of the slides here, you'll see that I have a series of problems in the back of the book. Those can only do you good. So doing the homework, drilling the homework will help you a lot. Looking at those problems that I designated there, that'll help you a lot. Doing the exam 2 that I gave you yesterday and also the other one that's online will give you an idea of the level of difficulty that's coming for exam 2. Yeah.
Are those new reactions? Or?
Yep, so I'm about to talk to them. Yep. So I think by the end of it, we're gonna add another 12 reactions by the end of Tuesday, which will complete basically alkynes. Much of the chemistry is the same as what we did with alkenes, and so that's the reason why I can kind of move a little quicker through it. It's just we get a different intermediate. Okay. Okay. Chapter 9. So what we started with alkenes as 1 unit of unsaturation, we're now going to work with alkynes, which has 2 pi bonds. So the very beginning of it is an alkyne is a hydrocarbon that contains carbon-carbon triple bonds, meaning a single bond and 2 pi bonds are involved. Acetylene is the simplest one. That means I have no alkyl substituents on it, and I have a 2-carbon alkyne with hydrogen on either side. This is the name for this would be acetylene, which is the simplest alkyne. And if I had a series of alkynes in a row, that would be called a polyine, which would be a linear carbon chain of sp hybridized carbons. This sp hybridization opens up all sorts of interesting chemistry while still being responsive to what happened with the alkenes. Meaning, we're talking about the reaction of pi bonds in general. And this compound has 2 of them. So the same reagents that we use for alkenes end up coming back for alkynes and creating these really interesting products. And of course, just to remind you, the acetylene molecule, and of course, because of that sp hybridization, it is linear. So an alkyne will always have a 180-degree bond angle between the one carbon to what's bonded to the other carbon. In this particular case, again, because we have these pi bonds, the pi bond in acetylene requires 202 kilojoules per mole. That's less than the amount of energy required to break the bond in ethylene, which is, of course, the most simple alkene. So this would be the structure for ethylene. Breaking this bond is 269 kilojoules. Breaking that first pi bond is 202. So what does that mean? It means that alkynes will react a little bit quicker with electrophilic reagents than alkenes will, but the same types of reactions are still possible. It's just that that extra pi bond becomes particularly reactive. So of course, as we start out, there's a nomenclature piece of this. So in general, everything you've learned with hydrocarbons still stands. That's the first part. So you can feel good about that. It's just the fact that if there's an alkyne in there, you replace the suffix with "ine." Instead of "ene" for alkenes, "anes" for alkanes. And of course, you want to number the first alkyne carbon in the chain is used to indicate the position of the triple bond. So what I want to highlight here, and I think these are 2 great examples of it, is who wins if I have an alkene and an alkyne in a structure? Which way do I number 1 versus not numbering it 1? And so in this particular case, what happened? We have an alkene and an alkyne at equal distances on that chain. Who won? The alkene did. Okay, so then what does that mean? It means that if you have an alkene in a structure and an alkyne, and the alkene and alkyne are equally distanced, the alkene is what is numbered as 1, just like what we did in the alkene chapter for nomenclature. However, if we now have an alkyne and an alkene, and now we see we have an alkyne on the end, and an alkene is now internal by 1 carbon, that the alkyne now gets the first numbering. And again, just like alkenes, the lowest number, we're encompassing the alkene within the parent chain. So in that case there, it would be 1, 2, 3, 4, and then 5, 6, 7, 8, 9. So in this case, it would be 4-methyl, 7-non-enol, which is the non-ene part of this, 1-ine. So life didn't get that much more difficult. All I'm saying here is that when you have an alkyne or alkene, alkenes take the numbering precedent compared to alkynes if they're equally spaced. If they're not equally spaced, then whichever one is encountered first gets the lowest number. And because now we've introduced this last functional group, and this will be the last one for the unsaturation part of 313, we now have 3 potential alkyl groups that can come off of these parent chains. The first one, of course, on the left is an alkane or N-butyl, meaning normal butyl, where we have 1, 2, 3, 4 carbons. If we were to replace one of those saturated carbons with an alkene, that becomes 1-butenol, where now the 1-butene would start with the nomenclature, and if we now have an alkyne, it becomes 1-butynyl, where now we have still 4 carbons, but the 1 would encompass the lowest numbering because the alkyne is there. Okay, so with all that being said, name the following alkynes. Okay, so what do we do? Parent chains, that's the first one. So we got CH3, and then C, CH3, H, and then this would be C, triple bond C, and then C, H, CH3, CH3. I think that got it. Next thing I do, find the parent chain. So that one, I'm going to call it this way. 1, 2, 3, 4, 5, 6. I'm going to make sure that the alkyne gets the lowest numbering. Unfortunately, from either side, it's symmetric. So 3 would be on either side of that. So I'm okay with that. Once I've named the parent chain, then I number the methyl substituents that are coming off of it. So in this case here, this would be 2,5-dimethyl, 3, 1, 2, 3, 4, 5. This would be hex-ine. That would work for me. Or 2,5-dimethyl hex-3-ine, if you want to go that way, whatever you want to do.
Oh, it's true.
Okay, how about this one? H, C,
Yeah, it is different.
triple bond C, and then this would be CH3. Oh, there's another carbon there. So C, CH3, CH3, CH3. I have branching this way, but now if we have any unsaturated compound, remember that has to have the lowest numbering if it's there, if I had to compare one side to the other side. So that means then this would have to be 1, that would be 2, that would be 3, we'll call that one 4. So what have I done? I've identified the parent chain. I then look for what groups are hanging off of that parent chain, and then I name accordingly. So in this case here, this would be 3,3-dimethyl. And I can leave the 1 off, but I'll put it in. So 1-butyne. Because this would be methyl ethyl propyl butyl. Yep, what's up?
So we don't have to, like, on both of those, we don't have to include the 3 or the 1 before the name, or we definitely do.
You need to do the 3 for sure.
No, I meant for the first one, like 3-hexene. Like, do we
Hexine.
have to,
Yeah.
yeah, hexine, do we have to specify always, like, where the triple bond is?
Yes. So in this case here, because that triple bond is internal on the molecule, you have to tell me where it starts in the molecule. The only time you can get away with not telling me that is this. So I would also take this as a completely correct answer. So dimethyl butane. And what you're telling me is that it's 1-butane if you leave the 1 off. If you don't put the 1 there, then and it's internal, then you're not going to get the right name back. Okay, good. Okay, yeah, what's up? Oh no, were you just stretching?
Oh, no.
Yeah, okay, okay. Yeah, what's up?
You can also say put like the one of like the new limit was build one ion or not.
Yeah, I would take it. Yeah, so this one here would be 3,3-dimethyl. Oops, let's make that all one word. But 1 I'm cool with that too. Yep. Okay. So the first thing we do in the alkyne chapter is now building upon what we did with alkenes, in the sense that we need to make alkynes, because that's going to be potentially a starting material that we can use for other reactions. So in the very first set of reactions, we deal with the pathways in which we can create an alkyne. And they all come from reactions that are called elimination reactions. So elimination reactions, which means we're eliminating something at the end of it. Our mechanism is we're kicking something away from the molecule to come up with our final molecule. So in this case here, so I'm going to now shorthand phenyl rings. So this, in my drawings, I'm now going to use this. This is an organic chemist shorthand for phenyl rings. It will make you faster on exams, because I'll also take this if you're going to draw me back structures as a phenyl ring, assuming nothing's happening with it. So all I'm saying here is I'm going to shorthand this next structure using that, replacing this. So that structure on pathway 1 would look like this now. So that would be this. See, we have a trans alkene. And what you can do is you can do a bromination reaction, just like what you guys know for the alkene chapter. So if we put in bromine plus some solvent, in this case it's methylene chloride, what that does is it of course brominates the alkenes. So that leads us back to a 1,2 dihalide. Br, Br, phenyl, H, phenyl, H. This will speed up your note taking too, by the way. So if you want to replace the, in 314 you have to do phenyl rings. In 313 you don't do anything with these. So this is a good way to kind of get faster. So we get a 1,2 dialkyl halide back from this. We knew that. We've already done the alkene chapter. So how do we get an alkyne? Well, what we do is we then expose this to 2 molar equivalents of a strong base in some sort of alcohol solvent. So this would be in ethanol. And what this does is a double elimination, and it leaves us back with the alkyne. That leaves the phenyl rings on it. So what's the mechanism for this? And I'm only going to draw the mechanism for this reaction here, just to sort of highlight the difference of what's happening with alkynes. So I'm just going to do the mechanism for that last part, the double elimination. Okay. So we have the CH halide, CH halide. Okay. So the first step here would be we have a strong base that we've added to solution. And so as a result, we can deprotonate this molecule. So we can come in, remove a hydrogen from here. That forms a double bond to there. And as a result, that then eliminates the halide on the other side, because that halide is what really wants the electrons. It wants to leave. It wants to take those electrons. So by doing this, we've created water, plus now what ends up being a vinyl halide. So in this case here, we would get back bromine there, hydrogen there, and a phenyl ring there. Now, the reason why I'm drawing the trans intermediate here is because when I do this particular reaction, there's a moment where this molecule has enough time thermodynamically to arrange to the most stable form of this alkene. And of course, trans alkenes are more stable than cis. So we get back the trans-alkene here. And then what occurs, so why do we have to use 2 molar equivalents of hydroxide? Is because it does a double elimination, meaning that another mole of hydroxide is required to come and remove the vinyl halide, meaning I have a halide directly connected to the alkene. And this, of course, results in our final alkyne. So the first part of this, nothing new, right? You guys already have that reaction in your pocket, where we have alkene to make a dihalide. But now you can make a dihalide, and if you expose it to base, you can double eliminate the halogens off of there to create alkynes. That's one way to do it. Any questions with that? Yep.
So on the exam, are mechanisms also a big thing, or are we focusing more on you giving us something and we're just giving the reaction? Like, are we gonna have to draw a lot of mechanisms, or
There'll be just one
just one mechanism?
that I'll specifically want to see arrow pushing.
Okay, gotcha.
But to that question, like every one of these reactions has a set of arrows that leads to certain stereochemical and regiochemical products, which means that really you're pushing arrows the whole exam because you're trying to rationalize why you're getting back cis or trans alkenes. And so that's where that reaction sheet really comes in handy, because the notes that you put there allow you to just make that product instead of pushing all the arrows for it. Yeah. Okay. How about this second way? So let's see. Now that this was a particularly nice and or nasty example that McMurray used to describe this. So what about this other piece? So if we have an alkene and we have a dihalide, we can do it twice. Well, if you have a vinyl halide to start with, we just need some base to kick it out. So in this case here, this is for path 2. We have here a vinyl halide. So in this case, we have chlorine as our leading group. We have a CH3 here, and we have a CH2OH there. And in the first step, he's using 2 moles of sodium amide. 2 moles. And then in the second step, he has some sort of acidic workup. Before we answer this one, let me do a slight variant to tell you the answer to this, and then we'll go back to this one. So why, the question I'm going for is why 2 moles? So we have CH3Cl, this is another problem. This is now an H, and this would be now a CH3. So if I had this alkene, this vinyl halide, meaning I have a chloro or a halogen directly connected to an alkene, if I came in with now just 1 mole of sodium amide, this works just great. Meaning that, and then some sort of acidic workup, oh no, we don't need the acidic workup on that one. This, of course, creates the CH3, C triple bond C, CH3. Okay, so again, this is just the second step, but now we're starting with the vinyl halide. So if we have this alkene, I need just 1 mole. And of course, if we were to draw the mechanism for this, C double bond C, CH3, Cl, H, CH3. What ends up happening, I see that sodium amide would be a relatively strong base. I could actually give you pKa numbers to tell you how strong it is. But what occurs, of course, is an elimination. So the hydrogen is attacked, the triple bond is formed. As a result of that, the chlorine gets kicked out because it's an elimination reaction, which then results in that alkene product. I'm sorry, that alkyne product. So why 2 moles? And because we're short on time, I'm going to tell you, it's because you have to be aware of your reagents and what types of functionalities are there. So in this particular case, that alcohol is a relatively acidic group. And so when I add this base doesn't go after that H. I can actually tell you. So the pKa of that hydrogen there is 35. The pKa of that hydrogen there is 16. I'm adding a strong enough base that I can actually deprotonate this pKa at 35. The trouble is, I also have a group that will react with that base even more readily. So the first mole in this, leads to an intermediate that looks like this. The first piece would be this, CH3, H, CH2O minus. And of course, chlorine's over here, and as a result of this, we end up blowing out ammonia, because NH2 reacting with a hydrogen would give us ammonia. And so this is the first species. That's where that first mole is needed. And then with the second mole, so NH2 can now attack here and do the double elimination. I like to use this example because this is probably one of the first examples where you have to start building chemical intuition with what you're seeing and the type of reagents that are there to know what type of reaction is going to occur. Let me give you an example of this. You know what? I think we'll do it next time. We'll do it on Tuesday. I know we're not going to make it all the way through Alpines, so we'll see what happens Tuesday. You should be able to do all the homework questions, though, so you still should be good. See you then.
Did the test?
Test is Thursday.